Good day. Welcome to the 14th lecture of metal forming. In the last lecture, we discussed the slab analysis of forging method, and we discussed how much amount of force or how much amount of average pressure is required for the deformation of the rectangular workpiece under plane strain condition. And we also study the distribution of the pressure during the metal forming, and that distribution is called friction hill. So today in this lecture, we are going to continue the portions or the analysis from the last lecture. And here in this lecture, we are going to study the slab method for solid cylindrical workpiece. So in the previous analysis of the slab method, that was a rectangular workpiece in plane strain condition. But here it is a solid cylindrical workpiece. So here we can see a solid cylindrical workpiece here with a initial height h0 and a diameter d0, and after forging it is reduced to h height and a d diameter. So during this reduction of height, we need to apply some amount of force and our average pressure. So this analysis actually helps to find out the pressure required for the forging of the cylindrical workpiece. For that, I take a very small element from the workpiece. You can see this yellow shaded element, and this is the enlarged view of that element. And this element has an included angle of d theta. It has a thickness of h. Okay, thickness h, and it has a radius of r. And in this element, I take a very small element with a dx thickness that is at a distance x from the center. At a distance x from the center, I take a small element for the analysis. It has a thickness of dx, and so this is the corresponding element. This element is the enlarged view of this element is shown here. And similar to the previous slab analysis of a rectangular workpiece, here also different types of stresses are acting on this element. And here the vertical force is acting, that is sigma z, the vertical stress that is equal to sigma z, and a horizontal stress is acting in the radial direction. In the radial direction, the sigma r, and in the one direction, and in the opposite ways of the element, dr sigma r plus d sigma r is acting. And the third one is the friction between the workpiece and die. So the friction force, we know friction force is equal to, or friction stress is equal to, we can say mu into the normal stress, that is equal to sigma z. So we can say the mu into sigma z is the friction stress acting on the surface or at the interface between the workpiece and the die. So similarly at the bottom also we have a mu sigma z amount friction stress. So these are the different types of stresses acting on the element. So here the analysis is or the derivation of the calculation for the calculation of the force as well as the average pressure is exactly similar to the rectangular workpiece slab analysis. So I am not going to explain the derivation and analysis area. And when we here in this also we in the radial direction, we balance the all forces in the radial direction. So first we convert all the stress values into force. So in the, we can say in this radial direction we have sigma r plus d sigma r, and the mu sigma z. In the bottom area also we have a mu sigma z. So all these forces are can be it is in equilibrium. So we can balance each other, and we can write an equation of the balance or equilibrium equation we can write, and from that we can calculate the pressure distribution. Okay, so by at the end of this derivation we got a pressure distribution equation, that is sigma, here this is not sigma y, this is sigma z, because in this figure it is given sigma z. So this is sigma z. Okay, so sigma z, or we can say the vertical force is equal to sigma y. Okay, anyway, the vertical force from the die to the metal, that is equal to sigma z, or the pressure is equal to sigma f into, that is equal to sigma f into e raised to 2 mu by h into r minus x. This is the amount of pressure developed on a workpiece during the forging process. So here also we can see with respect to the x value. What is the x value? Here in this equation we can see the x is the distance from the center to the element. So when we consider another element here, the x is vary up to this point. And so we can say when the element is here at the starting point, the x value equal to 0. When the element is here at the end point or the surface of the cylinder, then x equal to r. X equal to r. So the x value is varying from center to the surface. It is varying from 0 to maximum r value. So with respect to the variation of x, the pressure also will vary. See this in this equation, with respect to the x variation, the pressure also will vary. So we got a distribution similar to the previous case in the cylindrical member. We got a distribution for the pressure or sigma y. Sorry, sigma y. Okay. So the distribution is similar to the previous case. So and when we compare the equation, we can see here the P is equal to sigma y, sigma dash f into 2 mu a minus x by h. Here in this equation 2 mu r minus x by h. So the only difference is that here instead of r in the rectangular element we use the term a. That is the only difference. So in a cylindrical element or workpiece we use the term radius r in the equation, but in case of a rectangular member, here the distance from the center to the surface a is taken here. Here it is a, in the cylindrical member it is r. And one more difference is that here we use sigma dash f. Sigma dash f. That is the flow stress corresponding to plane strain condition, which is equal to 2 by root 3 of flow stress at a particular strain. That is equal to sigma dash f. But here in this case, sorry, in this case it is sigma f, because this is not a plane strain condition. So here we take only sigma f. We are not taking sigma dash f. Okay, so that is another difference. So the only difference is sigma f and the r value. That the remaining terms are same. And that is that by using this pressure formula we can draw the pressure distribution, and you know when the r equal to when x equal to 0, then pressure will be maximum. The x is equal to 0 at the center, so the center region is the region where pressure is maximum, like the previous rectangular workpiece case. And similarly we can calculate the average pressure also. For the average pressure there is a difference. Here in this rectangular workpiece, the average pressure is not the case. The average pressure is equal to this much. Sigma dash f into 1 plus mu a by h. 1 plus mu a by h. But here there is a variation. Here 1 plus not mu a by h, 2r by 3h. Okay, so instead of mu a by h, in the previous rectangular workpiece, it was mu a by h, 1 plus mu a by h, but here instead of a we use 2r by 3. So that is a difference. Okay, so when we compare this pressure distribution, average pressure in the case of cylindrical workpiece and this rectangular workpiece, we can see the difference. And here also instead of sigma dash f, here we use sigma f. This is not a plane strain condition, so we use sigma f. Then from this we can calculate the forging force, that is equal to average pressure into area. Here the average pressure is acting on the surface. The area of the surface is equal to pi r square. That is the area of the surface. So P average into area equal to forging force. So these are the equations for cylindrical workpiece. We can derive all this equation similar to the previous analysis, slab analysis of a rectangular workpiece. We can derive this equation. The pressure distribution, first formula is for pressure distribution. second formula for average pressure, and third formula is the amount of forging force required for the forging of the cylindrical workpiece. And here the H is the instantaneous height, and this sigma F is the flow stress of the material. And if the material is a perfectly plastic material, instead of sigma F we use sigma Y. Sigma Y is used, yield strength of the material. But if the material is a strain hardened material, we use the flow stress of the material in this equation. So here in this graph we can see the variation. What is the influence of mu? Mu we can see in this, and of course the A by S ratio. A by S ratio in case of this rectangular workpiece, that is the aspect ratio of the rectangular workpiece, and this R by S ratio in case of cylindrical workpiece. So we can see there is an influence for A by S ratio. A by S ratio has some influence on the pressure. Here we use P by sigma dash F. Okay, here we are not in the vertical ordinate, we are not plotting pressure average. Instead of that, we plot pressure average divided by sigma dash F. What is the importance of dividing with the sigma dash F? So when we divide with the sigma dash F, we can neglect the influence of strain hardening. So here if we use P average only, then for this variation, there is an influence of strain hardening. To neglect the influence of strain hardening, we convert this ordinate into a dimensionless term, that is this P average divided by sigma dash F. So here we can see with respect to the variation of A by S ratio, that is A by S means this for a rectangular workpiece, this is 2A, this is height H. Okay, so this is the aspect ratio A by S, and with respect to mu, we can see the variation of pressure by sigma dash. So when the P equal mu is equal to 0, that means there is no friction between the workpiece and the die interface. We can see for any A by S ratio, we can choose any A by S ratio. There is no variation in the pressure. This is a constant line, horizontal line. There is no variation in the pressure average. But if there is any coefficient of friction mu, then A base ratio has an influence on the pressure average divided by sigma dash F. With respect to increasing A by S ratio, we can see the amount of pressure requirement is increasing. Okay, and again the influence of the A by S ratio again increase if we increase the mu value. For in case of higher mu value, the significance of the A by S ratio is very high. Okay, so we can see the pressure increasing is more rapid or more steep under mu value when A by S ratio is increasing. So here we can see when mu equal to 0.2, we can see a sharp increase in pressure. The pressure required for the forging is sharply increased. Okay, so this is the variation in the case of rectangular workpiece. Next we can see a cylindrical workpiece. The similar thing we can see in the cylindrical workpiece. Here we use R by S ratio. This is the aspect ratio in case of cylindrical workpiece, radius by height. Here we can see this is sigma F, not sigma F dash, because for a cylindrical workpiece we are not considering a plane strain case, so we only take flow stress. Similar to the equation here, in the equation also we take sigma F, but in here sigma dash F, because in a rectangular workpiece we consider a plane strain case. That is why the von Mises criteria has to convert into sigma dash F. Sigma F is equal into 2 by root 3 is equal to sigma dash F. Okay. Here also we can see the similar variation in the pressure with respect to A by S ratio and mu value. For lower 0 mu value, there is no influence for R by S ratio. But with increasing the mu value, we can see there is a sharp increase in the pressure value. But when we compare these two values, we can see, for example, for 60, 60.1, 60.1 mu value, we got almost 7 P average by sigma f. But here for 60.1, we can see almost 12, greater than 12 we got. So higher amount of pressure is required here for a same value of A by S ratio and mu value. The rectangular workpiece required higher value of pressure to deformation for the deformation compared to cylindrical workpiece. And commonly in case of cold forging, the mu value is in between 0.05 to 0.1. But in case of hot forging, the mu value is in between 0.1 to 0.2. In case of hot forging, the mu value is higher. So that is this distribution. I will explain what is sticking condition later. The next analysis is sticking condition. So here from the derivations, in case of rectangular workpiece as well as in the case of cylindrical workpiece, there are three main factors which affect the pressure, which affect the amount of pressure or force required for the forging. Okay, three main factors. What are the three main factors? First one is friction. The friction between workpiece and a die. That is the first factor. The friction between die and the workpiece. Second factor is, this is ratio. Second factor is aspect ratio. In case of rectangular workpiece, it is A by S ratio. In case of cylindrical workpiece, it is R by S ratio. So with the increase in A by H and R by S ratio, we can see with the A by H and R by H increase, we can see there is an increase in pressure. So we should choose a workpiece with the lower R by S ratio. Then we can reduce the pressure or force required for forging. Third important factor is the flow stress of the material. We can see from the two equation, the flow stress has a direct influence with the pressure. If the flow stress of the material increases, then pressure also will increase. So choose a material with less flow stress, or we can do different heat treatments to reduce the flow stress of the material. Okay, if it is a deformed material, do annealing process, etc. Thereby we can reduce the flow stress of the material. So that is the three factors which affect the pressure or force required in the forging operation. The last analysis is the forging under sticking condition. Forging under sticking condition. Here we can see in this the friction force is equal to mu into sigma y. Mu into sigma y acting in this direction. Here also mu into sigma y is acting in this direction. This one. Okay. When a sigma y vertical force is acting on the sigma y vertical force acting on the workpiece. That is, for friction force is equal to, we know, mu n. So friction stress is equal to, friction stress we can say sigma f. Sigma friction stress is equal to mu into, here normal stress is equal to sigma y, so mu sigma y. So the mu sigma y is acting in this direction. See this, mu sigma y is acting in both interface region between the top die and workpiece, between the bottom die and workpiece. A mu sigma y is acting. So when we increase the sigma y value, what happened? This mu sigma y also will increase. Friction force increasing, because friction force or friction stress is the product of mu and sigma y. Okay, so when sigma y, the applied compressive stress is increasing, correspondingly the mu sigma y also will increase. So actually for this material, for the workpiece material, there is a ultimate shear stress value K. Okay, that means on the surface of the workpiece material, if the shear stress value on the surface of the material, if it is greater than K value, that is a critical shear stress. If it is greater than K value, then there will be a shear in the surface of the workpiece. There will be a shear in the surface of the workpiece. What happened? The one layer of material shear off. when the shear stress acting on the surface of the workpiece is greater than the K value. K is the nothing but it is the shear stress corresponding to or critical shear stress. Critical shear stress. Okay, and we can say if the flow stress of the material is equal to sigma F, if the flow stress is sigma F, then we can say K is equal to sigma F by 2. Okay, this is the half of the flow stress of the material. So that is the critical shear stress of the material. And when this mu sigma y, actually this mu sigma y, we can see the mu sigma y is acting on the surface in a tangential direction. So this is actually shear stress. So when the mu sigma y value is equal to the shear stress or critical shear stress of the material, then we can say this is a sticking condition. This is called sticking condition. What is the meaning of sticking? Is there any sticking between the workpiece and the die? No. But when this mu sigma y value is equal to the K value, that is the critical shear stress of the material, then there will not be any relative movement between the workpiece and the die. There will not be any relative movement. Both the workpiece and the die will not have any relative movement. Okay, that is called a sticking condition. Okay, so next we are going to analyze the sticking condition. So forging under sticking condition. So here mu sigma y is the frictional stress acting at the interface between the workpiece and the die. And when we increase the sigma y value, the mu sigma y also will increase. And the value of mu sigma y will not be greater than that of the shear yield stress or critical shear yield stress of the material. That is K. And the K is equal to sigma dash F by 2 in case of rectangular workpiece under plane strain condition. If it is a cylindrical workpiece, it is equal to sigma F by 2, not sigma F dash by 2. Okay. And what is the sticking condition? The mu sigma y equal to K value. That is shear stress of the material. Shear yield stress of the material. That is equal to K. Okay. So when mu sigma y is equal to K, then there will not be any relative movement between the die surface and the workpiece surface. That is a sticking condition. Under the sticking condition also, we have a pressure distribution. Under sticking condition, the pressure distribution will be different. Okay, so we can also derive the pressure distribution formula similar to the slab analysis of rectangular workpiece, and we got this equation. The sigma dash of into 1 plus a minus x by s. That is the sticking condition pressure distribution under sticking condition. Here again we can say with respect to x value the pressure will vary. When x equal to 0, the pressure has a sigma dash of value. When the pressure x is equal to maximum, then there will be a pressure value. So the pressure value will vary. And similar to this is the case of a rectangular workpiece in plane strain condition. This is the case of a cylindrical workpiece. In case of cylindrical workpiece, the pressure distribution is equal to sigma F. Here it is sigma dash of the sigma dash of that is the plane strain flow stress corresponding to plane strain condition. Here this is a flow stress into 1 minus. Here A is replaced with the R in case of the cylindrical workpiece. So 1 plus R minus X by S. So these are the two equations for the distribution of the pressure across the workpiece under sticking condition. Okay, so we can plot this pressure distribution by varying the value of X. And this is the plot by varying the value of X. This is the distribution. And here we can see compared to the previous distributions, here the curve is an exponential curve. But here we can see the curve is not an exponential curve, it is a straight line curve. It's a straight line. Okay, because here we can see there is no exponential term, e raised to nothing. Okay, so this will be the final equation distribution is a straight line distribution with respect to this x value variation. The x value variation, we got a distribution of p, and this is the distribution. Here at this tip it is maximum, at the two extremes edges it is minimum. Okay, that is a distribution. Here also we divide with the sigma dash of for converting into a dimensional state. So that is about the sticking condition, and this is the distribution. Similar friction hill we can see in the sticking condition also. So far we discussed the three analysis. The first one was the plane strain condition of a rectangular workpiece. Second one was the derivation or cylindrical workpiece, the forging load and average pressure or pressure distribution of a cylindrical workpiece. Third one was the sticking condition. So there may be a problem in these three areas to calculate the average pressure, the forging load calculation, the average pressure in the cylindrical workpiece or forging force in the cylindrical workpiece, normal pressure distribution in a workpiece with the rectangular workpiece with the sticking condition, cylindrical workpiece with the sticking condition. So these are the different problem types of problem may ask in the exam. So next I will do one problem related to these formulas. A rectangular workpiece. We have a rectangular workpiece. This rectangular workpiece has a following original dimensions 2a. So this 2a is equal to 100 mm and height is given, that is 30 mm, and width is equal to 20 mm. The material has a strength coefficient, that is K value is given 400 megapascal. N, the strain hardening exponent is given 0.3, is being forged in a plane strain condition. This is a plane strain condition, so we should use this equation. Sigma dash f is the flow stress corresponding to plane strain. So we should calculate the sigma dash f from sigma f. The equation is this one, 2 by root 3 sigma f. And mu is given 0.2, and calculate the force required at a reduction of 20%. So percentage reduction on this workpiece is 20%. Okay. So reduction is 20% means initial height was 30. So 20% reduction is equal to 6 mm. Okay. So the final height will be 30 minus 6, that is equal to 24 mm. 24 mm. Then we can calculate the true strain. True strain equation is equation number 3. We already studied log natural logarithm of final height divided by instantaneous height, or initial height divided by final height, instantaneous height. Okay, so 30 by 24. So we got 0.223, that's true strain. And then this is a strain hardened material, because here the strength coefficient and strain hardening exponent is given. Okay, there is a strain hardening there. Since this strain hardening exponent is 0.3 and the strength coefficient is 400 megapascal, that means there is a strain hardening. Okay, so we need to consider the strain hardening, or we need to consider the flow stress of the material during the when we do the problem. So we can calculate the flow stress of the material using this formula. Sigma f is equal to k epsilon raised to n, where k is given, epsilon is already calculated, that is a true strain, n is the strain hardening exponent. So using this formula we can calculate the flow stress. And again this is sigma f, but in case of plane strain we need sigma dash f, because in the plane strain equation we use the term sigma dash f. But in case of cylindrical workpiece, if this one has a cylindrical workpiece, we need only sigma f. We don't need to convert sigma f to sigma dash f. But here this is a plane strain case. We can convert this. We should convert this sigma f to sigma dash f using these equations, 2 by root 3 sigma f, and we got sigma dash f. Okay, then we can do here we don't know the initial length is given 100 mm, but after 20% reduction we don't know the final length. The width is constant. This is the plane strain condition, so the width will be constant. There is no change in the width, but when it changes from 30 to 24 mm height reduction, there will be an increase in 100 mm. So how much is increased? To calculate the increase, we can consider the volume constancy. So volume is constant here. There is no removal of material. So volume before forging is equal to volume after forging. So volume before forging is given, and volume after forging, from the in this A1 the length is unknown. From this we got 62.5. That is the final length of the product after forging. Then we can calculate the force, that is equation number 20. We already discussed this. P average into 2A into 2A1. 2A1, that is the final length into width. Width is not, there is no change in the width area. Then pressure average, this is the equation to calculate the pressure average for the rectangular workpiece. Equation number 26, we already discussed that. Substitute all the values. 294, that is the this value, sigma dash f. So 294 into 1 plus mu is given. A we already calculated here. In here it is in a meter. Already the reduction, the final reduction is already calculated, 0.24 mm. So from this we can calculate pressure average. By substituting pressure average into 2A into width, we can calculate the force required for the forcing. Okay, so this is the one type of problem. And another one is here we can use a cylindrical workpiece. This previous one was a rectangular workpiece here under plane strain condition. But here it is a cylindrical workpiece. Same way we can do, first calculate the strain, true strain, flow stress of the material. Then here we don't need to convert sigma f to sigma dash f because this is a cylindrical workpiece. Here we are not considering the plane strain condition. Already in the when we discuss the slab analysis of cylindrical workpiece, I already explained there is no plane strain condition in case of cylindrical workpiece. So we don't need to convert from sigma f to sigma f dash. We can directly substitute the sigma f value. Sigma f is 953 is substituted here, and mu value is given. All other values are given. We can calculate the pressure average. From that, we can calculate the force required for the forging. So similarly, you can do different problems. So you can do this problem. So that is about the analysis of and the calculation of the forging load in the under 3 cases. Next topic is the deformation zone geometry. So when we do a metal forming operation, so what are the different factors which affect the deformation, and what are the different factors which affect the deformation zone geometry? So we already discussed the pressure is proportional to A by S ratio, A by S ratio or R by S ratio, or R by S ratio in case of cylindrical workpiece. Okay, and this is because of the one reason is the friction. If friction is from this diagram it is clear. If friction is 0, see this, if the friction value is equal to mu equal to 0, there is no variation in the pressure. So there is no influence of A by S ratio under 0 pressure. Okay. So here, but when the friction is equal to 0, even friction is equal to 0, we can see from this diagram. Here instead of A by S ratio, actually for the forging operation, this is 2A and this is H. This is H. But here it is taken in this diagram, we are considering instead of 2A, we take L. This is L. And this is H. Okay, instead of 2A, here it is H, L. So, in the previous case, we discussed P proportional to A by S ratio. Okay. But this P proportional to A by S ratio is valid only when there is a friction. There is a positive value of mu. If mu equal to 0, then P is not affected with the A by S ratio. But here in this diagram, we can see instead of A by S ratio, the inverse is used here in the abscissa, that is S by L ratio. Instead of A, we use L. Okay, the inverse is used here. So here we can see the variation of pressure with respect to S by L ratio. Okay, so what is the reason for this variation? Here in this condition, here in this diagram, we consider that during every process, the friction is equal to 0. The friction force is equal to 0. So we consider different manufacturing process. First rolling, drawing, extrusion, breakdown rolling, forging, piercing, hardness testing. So in different manufacturing process, we can see the influence of S by L ratio when F is equal to 0, friction is equal to 0. There is no friction between the die and workpiece. When the even friction is equal to 0, there is an influence for S by L ratio in the pressure distribution. We can see in the harness testing, we can see huge amount of pressure is required for making indentation using a punch or die. Okay, so in case of this harness testing, the S-Bill ratio is very large value. What is the reason? So in case of this harness testing, you can see, okay, so this is the height, this is the height S, but this is L. So that the previous figure was bulk deformation. This is L. Okay. So in case of harness testing, the S by L ratio is very high. S by L ratio is very large in case of harness testing. But here in this rolling process we have a two rollers and we have a workpiece. This is a workpiece. Here we can see this is L. This value is L and this is S. So S by L ratio here will be lower one. That is why this is lower. S by L ratio is lower value. So this is the variation of the S by L ratio in different process. So when the S by L ratio is higher, we can see higher pressure is required for the deformation. So what is the reason for that? Here the friction is 0. We draw this figure or we plot this, conducted the experiment with the 0 friction. So what is the reason for this higher pressure required in the harness testing but lower pressure required in the rolling process when the friction is equal to 0? The reason is that when we do a harness testing to make an indentation on the surface, when we make an indentation, the actually the surface here, this is the surrounding region of this indentation. Okay, surrounding region, the material in the surrounding region. So when we do an indentation, the surrounding material offer a resistance against the deformation. The bulk material surrounding this indentation offer a resistance against the deformation. So because of the resistance, higher amount of pressure required in the case of harness testing. In the case of harness testing. But in case of rolling process, we can take the case of rolling process. In case of rolling process, the the entire material is deformed. So there is no extra material which is not in the undeformed stage to resist the deformed material. The entire material is deforming in case of rolling process. But that is not the case of harness testing. The undeformed material, this is only the region of deformation. So the undeformed material offer a resistance against the deformation. That is why the higher pressure requirement in case of harness testing, but lower pressure requirement in the rolling process. Even the friction is equal to 0. But when friction come into picture, we can say when the friction come to picture, here friction is proportional to, the pressure is proportional to A by S ratio, or we can say here we can give, instead of A we can give L. L by S ratio. It is proportional to L by S ratio. Okay, that is opposite of this case. Here with respect to S by L ratio, the pressure is increasing, but pressure is proportional to L by S ratio when friction is considered. That means if we consider the friction in the rolling case, that is a more contact area here, more length of contact compared to the height. Okay, so more friction, the amount of pressure required to overcome the friction is more here in the rolling compared to the harness testing. So that is actually the variation without friction and with the friction. How much is the pressure required in different manufacturing process without friction and with the friction. So that is explained here. The effect of friction at the die work, actually in the actual case, If in the ideal case no friction, then larger the S/L ratio, high pressure required. But in actual case, when we consider the effect of friction, then the friction increase with the S/L ratio. Friction increase. So similarly, the P value also will increase. By decreasing the S/L ratio. Okay, friction increases with the decreasing S/L ratio. That means in this region, we have high friction. This region we have low frictional force. Okay. So that is about the deformation geometry. Here we can see this is the bulk deformation of the mild steel and the spherical indenter. So these are the different manufacturing process. This is the extrusion process. In case of extrusion, this is the length of contact and this is the H value. Here length of contact is this much. This is H value. Here in this case, this is the length of contact drawing operation. And here this is the length of contact. This is H value. Okay. So in different manufacturing process, this SPL ratio is vary. Based on the SPL ratio, the pressure variation also vary. Okay, there is a pressure distribution. So that is about this lecture. In the next lecture, we will discuss about different uh, types of forging like impression die forging, closed die forging, and other miscellaneous forging operations and defects in forging. Okay, thank you.